Hello. Once again, you are about to watch one of the miraculous engineering examples of the Victorian era. Perhaps you have heard of this structure, and if you have not, you should definitely watch this video. In 1875, engineer Edward Leader Williams completed a hydraulic boat lift in Cheshire that raised canal boats 50 feet vertically between the Trent and Mersey Canal and the River Weaver. The wrought iron framework was designed to carry boats 3 times heavier than standard narrow boats. The hydraulic accumulators were sized for 10 lifts per hour, although traffic never exceeded 4. Critics described it as extravagant engineering for a minor canal connection. The original 1875 hydraulic rams operated until 1908, then were replaced with counterbalanced caissons, and later returned to hydraulic operation in 2000. Today, 149 years after its completion, the wrought iron structure remains unchanged, still lifting boats using Williams's original excessive load specifications. The lighter alternatives proposed in 1875 would have failed decades ago. The Anderton Boat Lift continues to endure. While watching this video, do not forget to press the subscribe button below. By doing so, you are not only supporting the creation of more content like this, a simple subscription shows that these words have reached you, and that the story of Victorian engineers who built structures for impossible futures means something to someone on the other side of the screen. So please like the video and subscribe to the channel. The Anderton Boat Lift solved a specific industrial problem in Cheshire. The Trent and Mersey Canal ran at a level 50 feet above the River Weaver. Canal boats carrying salt, pottery, and chemicals from the potteries needed to reach the Weaver navigation wharves, where larger vessels transferred cargo bound for Liverpool. The existing route required boats to descend through a series of locks at Anderton and then navigate a winding channel to the river. The journey consumed hours and limited cargo capacity. The Weaver navigation authorities wanted a direct vertical connection. Several proposals were considered: an inclined plane with wheeled cradles, a traditional lock system, or a hydraulic lift. The lift option was the most expensive and the most technically ambitious. The authorities chose it nonetheless. Edward Leader Williams was appointed chief engineer. In 1870, he had experience in dock construction and hydraulic machinery, yet had never designed a boat lift before. No comparable structure existed in England. Williams studied examples from continental Europe, but none approached the scale or capacity proposed for Anderton. He designed the lift from first principles, calculating loads, pressures, and safety margins without a tested precedent. The design specified 2 wrought iron caissons, watertight tanks that would hold boats and water suspended within a lattice framework. Each caisson would be moved up or down by hydraulic rams. The system would operate entirely on water power, with the weight of descending boats providing the energy to lift ascending boats. When you look at the technical specification, everything was generous from start to finish. Each caisson was designed to hold 1 narrow boat plus water, with a total weight of approximately 250 tons. Williams designed the structure to carry 750 tons per caisson. The wrought iron frame members were sized accordingly. The hydraulic rams were enormous. Each ram cylinder was 3 feet in diameter, with a stroke reaching 50 feet. The rams were designed to generate enough force to lift a caisson even if the hydraulic accumulators were depleted. This meant the steam-powered pumps could maintain system pressure during continuous operation even without the accumulators engaging. In effect, the accumulators were redundant, sized for peak loads that would never occur. Construction began in 1872 on marshy ground beside the River Weaver. Foundation work was difficult. The site consisted of unstable clay and silt above sandstone bedrock located 40 feet below ground level. Williams specified mass concrete foundations extending down to bedrock, with wrought iron columns anchored within the concrete. Excavation was done by hand. Workers dug foundation pits 40 feet deep while continuously pumping groundwater. The concrete was mixed on site and poured in stages, each foundation consuming more than 600 cubic yards. The wrought iron components were fabricated in Manchester and transported to Anderton by canal. Each major frame member weighed several tons and required steam cranes for positioning. The caissons were built as riveted wrought iron tanks with a rectangular section, fitted with internal bracing to resist water pressure when full. Each caisson measured 75 feet long, 15 feet wide and 5 feet deep. The walls were formed from 3/8-inch wrought iron plates riveted to angle iron frames. At the base of each caisson was a watertight gate, which, when opened, allowed boats to float in or out. The gate mechanism operated hydraulically and was synchronized with the lift cycle. For this reason, sealing systems were critical. Any significant leakage would create imbalance between the two caissons and cause unequal loading on the hydraulic rams. Williams specified rubber seals backed by multiple mechanical gaskets. Throughout its operational life, leakage rates remained negligible. The complexity of the hydraulic system exceeded anything previously built in England for this purpose. 6 hydraulic accumulators stored pressure, each a vertical cylinder containing a weighted piston. The accumulators maintained system pressure at 750 pounds per square inch, high for 175 standards. Steam pumps recharged the accumulators between lift cycles. The rams lifting the caissons were connected by hydraulic pipes to both the accumulators and the opposite caisson's descending ram. This meant the weight of a descending boat partly lifted the ascending boat, with hydraulic pressure compensating for imbalance. The system was elegant in principle, but required precise control to prevent jerking or uneven movement. Williams designed hydraulic valves that opened and closed gradually, producing smooth acceleration and deceleration throughout the 50-foot travel. The lift opened in July 1875. The first boats through were narrow boats from the potteries, carrying pottery to the Weaver wharves. The system worked exactly as designed. Each lift cycle took roughly 12 minutes, boats entering the caissons, gates closing, rams operating, caissons reaching their new levels, gates opening, and boats exiting. The process was controlled by a single operator in a cabin positioned midway up the structure. The operator managed hydraulic valves, regulating flow to the rams. Operation was smooth, quiet, and reliable. Traffic gradually increased. By 1880, the lift handled around 1,000 lifts annually. The lift's operational life was divided into 3 distinct mechanical periods. The original 1875 hydraulic rams operated for 33 years, with minimal maintenance. By 1908, the rams showed wear from continual use, but remained functional. The Weaver Navigation Authorities decided to replace the hydraulic system with a counterbalanced electric design while retaining the wrought iron framework. The rams were removed. The caissons were connected by steel cables passing over pulleys, with electric motors providing the small additional force needed to overcome friction and imbalance. This system operated from 1908 until 1983, but eventually the lift closed due to mechanical deterioration and declining traffic. The closure in 1983 appeared permanent. The electric motors were worn out, the steel cables required replacement, and the caissons showed signs of 108 years of corrosion. Commercial traffic on the Trent and Mersey Canal had fallen to almost nothing. The lift seemed destined to remain as a static monument. Then heritage restoration interest emerged. In the 1990s, the Anderton Boat Lift Trust proposed restoring the structure to full working order. Engineers assessed the structure and reached a surprising conclusion. The 1875 wrought iron framework was in excellent condition. The caissons were repairable. The original hydraulic design was superior to the 1908 electric replacement and could be rebuilt using modern hydraulic components following Williams's specifications. The restoration took place between 2001 and 2002. The caissons were removed, sandblasted, and repaired. New hydraulic rams were manufactured to Williams's original dimensions, 3 feet in diameter with a 50-foot stroke, using modern materials and seals. New hydraulic accumulators were installed, identical in size to the 1875 originals, but using modern pressure vessels. The wrought iron framework required only minimal intervention: cleaning, repainting, and replacement of a few corroded rivets. The 127-year-old structure remained fundamentally sound. The lift reopened in 2002, operating hydraulically exactly as Williams had designed it in 1873. Since then, it has run continuously, carrying recreational boats rather than cargo, but using the same principles and almost the same mechanism as in 1870. The survival of the wrought iron framework demonstrates Williams's over-engineering. The structure was designed for 750-ton caisson loads, yet it never experienced loads exceeding 250 tons. Frame members sized for triple loading have operated at one-third capacity for 149 years. This underloading explains the absence of fatigue. Wrought iron subjected to stresses far below its yield strength can endure indefinitely. Riveted connections designed for loads that never occurred show no deformation or loosening. Foundations driven to bedrock, where shallower piles might have sufficed, have shown no settlement. Every dimension criticized as excessive in 1875 proved essential to survival. Modern boat lift engineering follows different principles. Contemporary lifts use lightweight steel, precisely calculated for expected loads with safety factors typically between 1.5 and 2. Materials are selected for defined service lives of 30 to 50 years before replacement. Maintenance is planned around anticipated deterioration. These approaches work adequately when loads and usage patterns are known and stable. They fail when conditions change or when structures must operate beyond their original design life. The Anderton Boat Lift was designed with no defined service life and with safety factors greater than 3:1, built on the assumption that future conditions could not be predicted. The three mechanical systems that use the Anderton framework demonstrate different engineering philosophies. The 1875 hydraulic rams were overbuilt. Massive cylinders, conservative pressures, redundant accumulators, they lasted 33 years in heavy industrial use and were still functional when replaced. The 1908 electric system was optimized. Lighter motors, steel cables calculated for working loads, minimal redundancy. It lasted 75 years, but required increasing maintenance and eventually failed beyond economic repair. The 2002 hydraulic restoration returned to Williams's principles: conservative sizing, generous safety margins, and components selected for indefinite operation. The framework supporting all three systems remained unchanged. The only element built without compromise and the only one never replaced. The economic argument against the Anderton Boat Lift in 1875 was strong. The structure cost £48,000, whereas a traditional lock system would have cost £30,000. The hydraulic complexity demanded skilled maintenance. Capacity exceeded traffic needs by 3 times. A cheaper, simpler solution could have met immediate needs. These objections were valid when viewed only through the conditions of 1870. They ignored the reality that infrastructure built in 1875 would need to serve conditions in 1925 and 20. The lift that seemed excessive for 1875 traffic adapted to 1908 technology, survived abandonment in 1983, and returned to service in 2002 for purposes its builder never imagined. The cheaper alternative would have required replacement long before 1920 and would not exist today. Williams died in 1889, 14 years after the lift opened. He never saw the hydraulic rams replaced, the electric motors installed, or the structure restored. He built knowing the lift had to outlast the industrial canal traffic it served, the mechanical systems it employed, and the economic conditions that justified its construction. The 3:1 safety factor was not insurance against miscalculation. It was an acknowledgement that the future could not be calculated, and that structures serving unpredictable futures required margins that seemed unreasonable when conditions were known. Every boat rising 50 feet through the Anderton Boat Lift today does so because an engineer in 1873 refused to optimize for conditions he understood and instead designed for conditions he could not predict. The Anderton Boat Lift operates daily today, carrying recreational narrowboats along the Cheshire Ring Canal route. The 2002 hydraulic rams raise and lower boats exactly as Williams designed. The wrought iron framework flexes slightly under load, just as Williams calculated, and the foundations remain fixed in ground that has not shifted since 8. Here again you see a mega structure born from the intelligence of a talented engineer. If you would like more videos like this, please like the video and subscribe to the channel.